couple of years. Thank you.
Okay, thank you also. Thank you for inviting me, and it's a great pleasure to be here. Well, the work is a kind of application of the transfer function based on green functions. In this case, I will present the techniques applied to thermal parameter estimation. Specifically, this study presents an experimental technique to obtain the conductivity and thermal diffusivity of solid materials. In parameter estimation techniques, properties are found minimizing an objective function. This function is usually a square function error calculated from the experimental and theoretical values of temperatures. The difficulty is the presence of the local minima in the objective function when the parameters are correlated. So, in this case, the proposed estimates the properties separately, but using the same experimental data. It means heating and measurements of temperature and heat flux occur on the same surface. The methods use transfer functions in the identification to solve inverse heat conduction problems, and is based on Green's function and on the equivalence between thermal and dynamical systems. In this case, different objective functions are used to estimate the thermal conductivity and thermal diffusivity. Well, in fact, some difficulties appears when we are estimating some thermal properties that are correlated. For example, we have low sensitivity due small temperature. We have problems like contact resistance, and we have to develop the methods also thinking in the experiment, in the accuracy of the experiment. So the objective of this work is to determine simultaneously thermal conductivity and thermal diffusivity, and both materials, conductor and non-conductor materials. And we think to develop the thermal model and the experimental device. And we have to think, we're also thinking in situ application. So we have to develop the technique that we can use only one axis surface, okay? As I mentioned, the proposal here is based on the use of input and output dynamical system. The dynamic characteristic of constant parameter linear system can be described by an impulse response function, which is defined as the output of the system at n time to a unit impulse input applied at time tau before. For example, for an arbitrary input, the output is given by the convolution integral. And we can use the system using the transfer, the Fourier transform, and the response, the frequency response in this case is a complex number, but the integral convolution in the frequency domain is just a multiplication equation. So we intend to work with the data in frequency domain because it's very easier than the time domain to obtain the response of the system. In fact, if we have a complex number, so we have to work with two variables. In this case, we have a modulus, the absolute value that is called the gain factor of the system, and we have the associated phase angle that is called the phase factor of the system. This kind of dynamical system can be observed in so different systems. For example, we have mechanical. We can have a mechanical system, so you can put a force and observe a force as an input and observe the displacement of the system. Or in an electrical system, you can put as a voltage as an input, or even you can change and you can put the current, and you have the output of the voltage. So we can work with this expression in order to obtain the response of the system. This picture shows the relation of the various system. And if we have an electrical system, we have a voltage as an input, and you have the output, the current. So the response of the system will be in function of the inductance, resistance, and capacitance. If you have a mechanical system and a force as an input and velocity as an output or the displacement, you will have the response of the system in function of the mass, the damping, and the compliance. So this kind of system is equivalent if we have a thermal system. We can work in both of sides. We can use input of temperature and output of heat flux, or we can use as input the heat flux and work with output of temperature. In this case, the response of the system are in function of the thermal resistance and the thermal capacitance. So this is the idea that we use to try to use the procedure of the system, the dynamic system, in order to obtain the properties, because in dynamic is very common. You estimate the response of the system. In this case, we have in the thermal system equivalence, we have as an input the heat flux, and output, for example, in this case that I'm showing, the difference of temperature in 2 points of the thermal system. And in fact, we are working with this data in the frequency domain. that just using the multiplying the convolution. This case, we have, just to show, we have a sample in a 3D thermal equivalent model. We have a heat flux heating partially in a surface of the sample, and we have the two temperatures measured at two different locales. And it will be shown that if we have this kind of problem, we can obtain an expression that you can put in the same way of the dynamic system. So we have temperature, heat flux, and the response of the system. For example, if we have this kind of problem, the three-dimensional thermal model can be obtained by the solution of diffusion equation. And if all the boundary conditions are isolated, but just the heat flux on the specific region, and with an initial temperature, we can solve this equation with this boundary condition using the green functions method. So we can put we can obtain the solution just in function of the green function and the input, that in this case is the heat flux. The dependence of the green function in this case is in the T minus tau. So this is a convolution equation, and we can if we call the difference of theta, we can obtain in the frequency domain just the product of this difference of temperature with the heat flux and the green function plus the rate of thermal diffusivity with the thermal conductivity. In this case, if we work with the 16th equation, so we can call or we can, by comparing this equation, we can with this equation, we can see that the green function is the response of the system. Okay. So the Green's function is the response of the system, the frequency response of the system, and just can be obtained by the difference of temperature and heat flux after we take the Fourier transform. Okay. So if we measure the temperatures, and if we have measured the heat flux, we just take the Fourier transform and obtain the variables in the frequency domain. In this case, the heat flux, the transfer functions is as in this case, we have two temperatures. You have to obtain the solution for these two temperatures, and so the Green's function in this case is the difference of the Green's function for each for each position. So we can obtain the equivalent response in frequency just knowing the green function. Well, we know that the green function is strongly dependent of the thermal properties because the green function is, in fact, is the solution of the thermal problem. So we can use this as a variable to measure the thermal properties. And the idea is to use the modulus of the response in frequency and the phase factor in order to estimate. So we work with the imaginary and the real parts of the frequency, the response in frequency. Well, the question here is how to obtain the temperature without knowing the heat flux or without knowing the response in frequency, okay? Remember that we will work with the equation in the frequency domain, so if the heat flux is unknown, that's defined as an inverse problem, and if the response is unknown, that's defined as an identification problem. Well, the techniques based on transfer functions, it's initially developed to obtain the input, the heat flux input. But in this case, he is used in the same way, but just thinking and to identify the thermal properties of the response. Okay? So we are going to obtain the Green's function, in this case, the transfer function explicitly, and work in the phase to estimate the thermal diffusivity. Well, the Green's function can be obtained observing the types of bound air conditions in the three directions. We can have the condition, the first, the second, and the third type, independent. In this case, for example, if we have all phases are subjected to heat exchange by convection, except the region with the heat flux. So the Green's function for this kind of the problem can be given by the equation 26. And the analytical expression for the solution of this problem is quite bigger. And the great force of this technique is that the expression is in function of the heat flux, okay? So we can work with this, and if we have the heat flux, we have the solution of the direct problem. Well, ideally, we can put this heat flux symbolically as an impulse, a direct problem. in the direct problem. For example, if I put the impulse here, the expression can be the solution, because I can use the properties of the delta of Dirac, okay? So we can do this in order to obtain the response of the system. So if we put the heat flux as a data of Dirac, the temperature solution is the transfer function. So the transfer function, in fact, is the Green's functions multiplied by the rate of the thermal diffusivity and thermal conductivity. And we can obtain the transfer function without performing any integral, okay? Just using the Green's function. This method can be used in any type of heat conduction problem, 1D, 2D, or 3D, and with different types of boundary condition. The cruise of the method lies in identifying the impulse response transfer function for each particular problem of heat conduction, using the Green's functions that describe the problem. The phase of frequency response and the time evolution of superficial temperatures are the experimental data used for estimation thermal diffusivity and thermal conductivity. In this case, in a previous work, we have discovered that the phase factor of this transfer function just depends on the thermal diffusivity. So we can use the minimization of the phase factor in order to obtain the thermal diffusivity. Okay. It's easier because you have just only one variable in order to estimate the properties, in order to minimize the function. And if you have estimate the thermal diffusivity, you can use the modulus in order to obtain the thermal conductivity. So you can use in the frequency domain, or you can use in time domain, just using the temperature in the time domain. Okay. Some difficulties that we can solve with these techniques can be shown in this figure. For example, if you are working with conductor material, so you can have a contact resistance problem. If you use, for example, a 1D model, So if you use the 3D model, you can solve this problem of the contact resistance. And the other problem is, if you are working with conductor, you have to put a higher heat flux in order to obtain the gradient of temperatures. So if you put the same heat flux, you will have difference of temperature in order of the uncertainty. However, if you put if you work with the 3D model, you can put thermocouples here, and you have larger difference of temperature, and so you can obtain the thermal conductivity and the thermal diffusivity with more easily. Okay. Well, another important characteristic of this technique is that here we use some transducer of heat flux, but in order to estimate the thermal diffusivity, you in fact don't need to know the magnitude of the heat flux. So you can work with original data or calibrate data that the phase doesn't change. So it's another advantage of this technique. This only happen in the phase factor. If you are working with the model, so it's so different. Okay. Well, I will show some results. We work with three materials. A metal that is IC 304, and two polymers, PVC and polyethylene. The results for the IC 304 was obtained with our less than 2%. And this figure shows the comparison between the experimental estimated temperatures using the data and using the experimental data and use the temperature recovered with the thermal property estimated. And the polyethylene polyvinyl chloride, and we obtained the thermal properties for PVC and for polyvinyl. Here is the phase with the experimental and the phase calculated with the thermal diffusivity estimated, and the residues of the phase factor, and a comparison between the temperature estimated and the experimental temperature measured, and the residue of experimental and calculated data. And the same case for the PVC, we have thermal properties with error less than 2%. The conclusions, this work, the transfer function, which describe a given thermal problem, was obtained through analogies between the theory of Green's functions and dynamic system, and then applied to solution of inverse problems in heat conduction. The use of MATLAB is very interesting because you can work in the frequency domain, and this procedure gives a great flexibility in order to work with large materials with thickness, small or large thickness and dimensions, and work with conductor and non-conductor materials. And another great advantage is that you can use you can treat both models, 1D, 2D, or 3D models. Okay. Thank you for your attention.
Thank you, Gilmar. Questions?